Hey, what's going on, guys? Geeky here. So here is the output that we have from the previous part. We can print the hex dump, and in this video we're gonna write a couple of procedures allowing us to write a single byte to a certain memory location. So let's say over here or whatever location, doesn't matter. So 2 digits represent a single byte, so we need up to 2 procedures. So the first one that would be converting a single nibble from the ASCII character to integer, basically, and the other would be encoding the entire byte. So later on, so that byte, after being encoded, would actually get stored to the certain memory location where the I register is going to be pointing to. So a bit of initialization stuff is needed as well, but these 2 procedures are the parts of a bigger procedure of the main editor loop. But I just don't want to take everything in one run because it just takes too long. So just split, divide, and conquer, and that's the way to go. Okay, so without further ado, let's actually start. But before that, one thing that I was concerned about in the previous part. So we actually don't really need to say jump greater equals. So jump equals is literally enough here in the print memory line 29. So yeah, that was just from, we don't really need jump greater equals because we never exhaust the 32. Okay, so edit. Now we have exactly the same output. So just make sure to fix this. It's gonna be working as that, but just to be a bit more precise and neat. That's this should be jump equals, not jump greater equals. Okay, but even with the jump greater equals, it's still gonna be working. Okay, guys, so now here, well, let's say above or below hex to ASCII. Let's do it above. So we want to create a procedure to convert nibble to convert ASCII character to convert ASCII character to nibble, and this is the half of a byte. And we don't know for sure, like so let's call it ASCII to hex. Well, actually, it's not exactly it's to integer. It's not exactly like, doesn't matter to hexadecimal, to decimal, to but let's keep it like this. So the idea is that this particular procedure has no idea about whether this is the left nibble or the right or the upper or the down one. So it doesn't know. In order to compose the entire byte, we're going to be using the encode byte procedure, which we would run next. But this one is very essential because otherwise the encode byte would be working on the ASCII characters and not on the actual like byte values, let's say. So we really need to make sure that we convert this ASCII digit back to the integer, let's say. Yeah, so I know probably would it be better to say int to ASCII or ASCII to int, or well, but hex, just okay, let's keep it like that, basically. Maybe not the most accurate way, but okay, anyway. So, and here we need to do absolutely the opposite to what we've been doing here, right? So here we were doing the opposite, like converting the integer to the ASCII character, and here we want to do the opposite thing. So let's compare AL. So after we will, so we would be invoking the BIOS call to get a user input, a single key, and after that the AL register would be containing a key that user has just pressed. For testing purposes, we're going to be initializing that manually, but just to give you an idea, so AL would be containing the value of the key of the ASCII character that corresponds to the key that has just been pressed, and we need to convert this with the A. So it's the case for letters. So jump less. So if this is if the value is less than A, so this is just a hack. Actually, this is 97 in a decimal and I guess 61 in hexadecimal, right? So if the value is less, then we know for sure that user has entered a digit. So in this case, we just want to jump to the digit label. Okay, so let's say did user input digit or letter. Okay, so if digit, then go to converting to digit. Okay, and otherwise we are dealing with the actual letter. So in this case, we need to say subtract from AL and the value we're already familiar with. So A minus 10. So in decimal, this would be 97 minus 10, 87. But that's just a more user-friendly way of doing this. So here I just say otherwise convert to hex letter. Okay, so would it be well, it's not exactly, well actually the resulting value, like A would get converted to 10. So let's say A becomes 10, B becomes 11, and so on, and actually F becomes 15. Okay, so I hope it's clear. So this is what's going to happen after this operation. So this, like, the characters are getting converted to the corresponding digits. All right. So if we don't do this minus 10, then A would become 0, but we actually want it to be 10s, hence this minus 10. Okay, so yeah, what else? And here we actually want to return, right? And one last thing is to process if this is a digit actually. So if this is a digit, then we need to say subtract from AL and the value of the 0, which is 48 in decimal, and I guess 30 or 31 in hexadecimal, don't remember, it doesn't matter. So here we want to convert so actually convert ASCII char or byte, and here convert ASCII char to digit. So it's very simple here. So 0 gets converted to 0, and let's say 1 gets converted to 1, and let's say 9 gets converted to 9. So again, like, so at first, so this character, like in decimal, this is 48, which is not okay. So we need to convert 48 to 0. So we do this minus this value, and this is 48. So this would be 48 minus 48 minus 48, and this would be equal to 0. Okay, so that's how we get this 0. Okay, and then let's say for here we would have 49, which is 1 minus 48, and we get 1. Okay, so this is how this one happens, occurs because of this operation. Okay, sorry, so I hope that's clear. Okay, and yeah, that's pretty it. After we can just return from procedure. All right. Okay, so this is it regarding conversion. So one of the core parts, again, like from of the hex editor on its own, and now we want to create a procedure to encode bytes. So let's actually call it encode byte. All right, and here is the deal. So we're going to be using, now a bit of a convention, that's implementation dependent stuff. So that's how I'm doing this in this hex editor. So how do we know whether it's the first nibble or the second nibble of the byte? So I'm using DH register in order to distinguish between the first nibble and the second nibble. So there would be two cases. So if DH is equal to 1, this so we're going to be altering this DH. So every time user would be pressing the key, the DH would get incremented, and when it gets the value of 1, we know that we're dealing with the first nibble. If DH is going to be equal to 2, we know that we're dealing with the second nibble. Okay, and here in the encode byte, we would also reset the DH after encoding the entire byte. So that's how it works. So bearing on this, I need to say compare DH with 1. So let's say, are we dealing sorry guys, I want to make sure that I'm spelling the dealing properly. Just hold on a little bit. So are we dealing with, yeah, okay. So are we dealing with first nibble? Okay. Jump equals let's say nibble 1. If so, encode first nibble. Okay, and then comparing DH with 2. So here, are we dealing with the second nibble? And jump equals to nibble 2 respectively. So if so, encode the second nibble. Okay, and now what's going to be happening within this encoding? Something quite pretty similar to what we've been doing, well, I would say quite opposite to what we've been doing when printing. So remember, we have been, where is that print memory? Yeah, so you remember, so we've been extracting the first nibble and decoding it to ASCII, and then we've been extracting the second nibble and decoding it to ASCII. So now we need to do the opposite stuff. So here is the label for nibble 1. Okay, so nibble 1. So first we need to temporarily store AL, and I'm going to be using the DL here. So we have DH serving the purpose of like distinguishing between the first and second, the first and the second, whether this is the first nibble or the second one, while DH, sorry, not DL, while DH, or, oh, sorry, yeah, DH serves the purpose of distinguishing whether this is we're dealing with the first or the second nibble, while DL would be the temporary store for the current value of AL. So here we want to preserve the value of AL, so let's say temporary store AL. Let's have value from AL to DL, because then what we do, so we just shift left the DL by four elements, and this is what's going to be happening. So in this case, we know that we're dealing with the first nibble, so so this is what we have initially, okay? But we need this to put it here. So if we say shift left by 4, this would be like this. And you see like the actual value. So this 1111 represents the value of AL, and this is what's happening. So we want to make current AL value to be first nibble. To encode, we want, let's say, encode current AL value to be the first nibble. Okay, so yeah, probably we can just keep this, right? I just can't get rid of this. Yeah. And return after. That's pretty it. So return from the procedure. So for the first nibble, we're not writing anything to memory because we still need to wait for the second nibble to arrive. Okay, so here we have the second nibble. Here, and now we want to like initialize reset. So we want to reset DL. Okay. Sorry guys, what am I talking about? Reset DH, obviously, because DL is holding the upper nibble of AL. So resetting DH, resetting DH, because we know that we're in the second nibble, so we need to reset it. So the next ASCII digit that we encounter being typed from the user is going to be treated again like the first one. So yeah, reset DH, because the byte is now completed. Okay, and then we need to use the bitwise OR operation. So OR the DL and the AL. So the upper 4 bits of a DL. So remember, so DL is the 8-bit register, and we already have the upper 4 bits of the DL representing the first nibble that we've used from AL after left shift. And now all we need is to OR. So to make the bitwise OR operation between, so it's like 1 1 0 like this, and then OR with, so here we have, so this is the first nibble, this is the second nibble. Okay, so this is the first nibble which is stored in DL. This is the second nibble stored in AL. So probably, yeah, let's actually, as far as I have some space here, so it's first nibble in DL. Okay, and this is the second nibble in AL. So second nibble in AL, and eventually this would result in something like this. So FF eventually, and so we have F and F, and this byte FF would actually be stored, would actually get stored to the memory. So once we've done with that, we can then yeah, hold on a sec, this should be, oh, hold on a sec, I don't even need all of this. I can use another line for, sorry guys, yeah. So yeah, so we want to bitwise OR first nibble in DL and second nibble in AL, and yeah, this is what we got. This is what we got eventually, and store single byte, 1 to store the resultant byte. Yeah, hold on a sec, I forgot one little more thing. So store single byte stores the AX value, or AL, or depending on. So we need to say first move, oh, I'm sorry. Hold on a sec, let me just, it's quite important, let me refresh this properly. It stores AL, AX, or EAX. Store a single byte where the I is pointing to. Stores a byte, a word, or a double word from AL, AX, or EAX respectively. Okay, so store byte from AL, store a word from AX, and double word from EAX. Okay, so yeah, AL definitely. So whatever we have in AL would get stored to where the I is currently pointing to. So we need so now DL has the value of the byte. Okay, so DL holds the value of the byte, and now we put that value to AL. Move a complete byte value from DL to AL, and here we want to write value at AL to, okay, write the resultant byte stored at AL to where DI is pointing to. Okay, so this is the store single byte, and then we want to return from the procedure. Return from procedure, and that's pretty it, guys. So yeah, now we need to write a simple routine, not even a routine. Now we'll go and test how this works. So now we'll try to write a single byte. So do we have any errors? Okay, we have a couple of encode byte enable 2 undefined, encode byte 68. Oh, nibble 1, yeah, obviously let's call it nibble 2. Okay, 85 invalid. Oh, yeah, we should no column there. Okay, yeah, no errors. So now we'll try to write a byte of the first byte here at the address of 500th hexadecimal. Okay, I'm sorry guys, I'm just fitting my castle on the way, so a bit busy with this housekeeping stuff. Okay, so now let's go and test it. So let's do it here, and before printing the memory, so let's artificially create what we want. So let's put to AL, so let's say we want to encode bytes, say A and 4, so to have like one digit, one letter, one hexadecimal letter, one digit. So let's say put A to AL, and now we need to convert it to hex. So ASCII to hex. So here I call ASCII to hex, right? Okay. So now it should be like the integer value. So now not the ASCII value, but the integer value, or hex representation potentially. And to know whether this is the first enable or the second one, we need to initialize the DH properly. So this is going to be the first enable. So I just say move DH and 1, and then I can call encode byte, right? Encode byte, and the same thing for for a second digit, right? So yeah, for a second digit, they should be equal to 2. So let's say, just copy this. So here, just generally say I just want to encode first nibble. Encode first nibble. Here I want to encode second nibble. So here, let's say the value of 4. So just to give some numeric value there, and DH is going to be equal to 2. So after this, this should reset DH back to 0. We will need that within the loop. So we'd reset DH to 0 and also store a single byte. But in order to store it to the proper location, we need to set the DI pointer. So where to write to. So this is the write address, and move DI, and I want to write to hexadecimal 500s. So here at this address I want this byte. So if I did everything properly now, so this byte now should take the value of A4, and if it is, then we'll also, just to make sure that everything works properly, we'll also get the memory dump from the emulator, from the online emulator, to make sure that it's really there. So let's go for edit, and now we got A4. Fantastic. So let's try to do the same in this online emulator. So choose the file, tutorial, part 15, GameOS, open, start emulation. All right, so yeah, edit. So we got this A4, and now let's get the memory dump to make sure that at this address we really have this value of A4. We'll now inspect this manually by using the Linux. So let's just Linux hex editor to view that. So let's delete again. So memory dump. So it's downloading, okay. And open terminal, xxd and v86 memory.bin, and we're looking for an address 0500, and we got A4 here, guys. So this is absolutely fascinating, really fantastic, right? So we've just managed to write a byte to the certain memory location. So that's the very gist of the hex editor. Now the only thing left here to be completed is actually to write the main loop to that would be allowing us to type in the address to set up the DI pointer. So just what do we need to automate from now on? So from now on we need to automate the process of initializing the DI, because we can't assemble it every time, right? So we need to initialize this address from the user input, and we're going to be storing the address where DI is going to be pointing to eventually to here, to this write address. Okay, yeah, and by the way, we no longer need this sort of a thing. Okay, so we'll be storing the address of where to write bytes here to write address, and then we will enter the loop, allowing to enter the actual bytes. And the code that I've prepared for that sort of a thing is not really that most probably 100% great ever code, but it works. It's very simple and straightforward, and the most important thing that it still fits the 512 bytes. So that's really important thing to consider, because if we just say we can use this memory dump to see how big our editor already. So let's search for 7C00, so for the boot sector, because the editor is running in the boot sector, and 7 oh yeah, I'm not sure. Yeah. So these are the bytes that still remain here. Yeah, these bytes remain, and we need to feed the entire edit loop within this byte, which it will, it would be okay. So yeah, but that's gonna be the topic of the next tutorial already. So in the next video, guys, we're gonna be writing the editor loop, and hopefully the hex editor would be completed in the next video. And then the only thing that would left in order to make it running the x86 machine codes, we'll need to provide the run command, which would be that simple, just a loop from the shell to this location, right? And that's pretty it. And then we're going to be testing how it works. Well, okay, guys, so this is from my side. Hope to see you in the next tutorial when we would be implementing this main editor loop. So until then, and take care.